Thank you, Margot, and all the organizers. I think this is the second time I joined you, and it's just very inspiring to see all the women in data sciences from academia and industry and NGOs. So great honor to be here. As you know, I'm a professor at Stanford. My research focus in artificial intelligence, computer vision, and machine learning. I'm also on sabbatical this year at Google Cloud. You heard from Diane Green earlier this morning, working on democratizing AI for everyone and every business. So today I'll share with you a little bit more about what I do, artificial intelligence, especially from a research angle. I don't think I need to convince you that we have entered the age of AI. Everywhere we look, the applications and technologies of AI is already or going to impact every aspect of our life. So a little bit of a historical view about AI. You all know this man, Alan Turing. He was a cryptologist, mathematician, and working with the Allies during World War II. And it was Turing, among others, that inspired humanity with a very important question of how do we build intelligent machines. So Turing says that to build intelligent machines, it may be best to provide the machines with the best sense organs that money can buy, and then teach it to understand and speak English. So while back 60 years ago, Turing's hypothesis was mostly a wild imagination of a scientist and a mathematician, but he already talked about two really important ingredients that will guide modern artificial intelligence research and technology. One ingredient is sensing. Sensing is a very critical part of enabling any intelligent machines, especially collecting information from the world. In my world, visual sensing is a huge part of it. Of course, there is speech, there's haptics, and there's other parts of sensing. But vision does occupy a very special place in all of our brain. In fact, more than half of our brain, human brains, are involved in visual processing. It's the biggest sensory systems in the cortex. Another part of Turing's hypothesis is language. Language is really unique to humans, this complexity. And Turing hypothesized that in order to build that kind of intelligent machine, we have to solve the language problem. But Turing really, it was a wild imagination. He had a lot of ideas, but whatever he said was really only the first step. From that point on, it's been generations of researchers in AI that has been working on the problem of AI. And there's one local hero of mine that many of you probably don't know, and that's a Stanford professor called Terry Winograd. Some of you might know him. Terry is one of the first generations of AI researchers. He did his PhD at MIT with Marvin Minsky and many others. He then moved to Stanford, in fact, that after his AI research, he also was part of the pioneering scholars that brought up the field of HCI, human-computer interaction. But Terry is a very important figure in the history of AI. Before I say what his contribution is, I'm also very lucky he's my neighbor. So this is literally in front of our houses. So I feel like the value of my house, has increased because of Terry. So Terry operationalized Turing's idea of building this intelligent machine. He's not the only person, but he really, among many, was in that generation that started to put forward the 3 ingredients of building the AI machine, the intelligent machine: the syntax part, the semantics part, and the inference part. And for him, it's really important that the syntax, syntax is about understanding the structure, whether it's language structure or 3D layout structure, structure of the world. Semantics is the meaning of the world, the language or the objects, and so on. And inference is the prediction. And in one of his most celebrated work is a system called Charlu that Terry put together a demo system that included these 3 ingredients, mostly focusing on language. And this is the early work. It's probably one of the very first AI system that completes that idea of an intelligent machine, and it's called Charlu. And Charlu assumes, there's one big assumption: Charlu assumes vision is solved. We live in a simple block world, and it's where the language inference happens, where a machine will listen to a human instruction like pick up a red block, a big red block. The machine would look at the world, do its inference, understand there is a big red block, and lift it up. And then the human can give another instruction: find a block which is taller than the one you're holding and move it to the gray box. And then the machine, Charlu, would go through its inference again, parse the sentence and understand the structure, understand the syntax and semantics, and decide that the blue block is the bigger block and put it in the gray box. And it just goes on. I'm going to skip the next examples. So Charlu was really quite exciting in the 70s, along with a few other work in this block world that really showed us, wow, we can start to build machines that Turing was imagining. It's the machines that can understand human language and perform tasks. But to be honest, while it was pioneering that whole set of work, it didn't push AI beyond the laboratory demos. From 70s to 90s, we haven't seen the kind of progress that we wanted in artificial intelligence. And one of the biggest problems was actually hidden in the algorithms of the early systems of AI. And it was the rule-based, hand-designed rule for inference and very little learning. So this is not meant for you to understand, but these are examples of the rules hidden under systems like Charlu. And while it was okay for a block world that's heavily simplified, it has a lot of issues. It has a scalability issue. It's hard to anticipate all possibilities. For example, here's an example. If you talk to Siri, "Hi Siri, call me Fred," Siri would say, "Okay, I'll call you Fred from now on." But what if you say, "Siri, call me when you get a chance"? Well, the rule-based system would infer and think that when you get a chance is your name, and Siri would call you when you get a chance, and that's not what we mean. So scalability is an issue with hand-designed rules. Another issue is adaptability. When we design rules, we design it for a specific situation. For example, language parsing. We can design rules for English parsing, but how about Japanese or Chinese or any other language? And of course, hand-designed rules are very difficult to adapt for open world, especially when there are situations that are hardly unseen or unique. So these are the problems that kind of slow down the progress of AI going into real-world applications. Well, machine learning came to the rescue. starting the late 80s and 90s, machine learning become a blossoming field that really injected new life into AI. So for those of you who are not familiar with machine learning, here is a very simple summary of the difference between traditional rule-based programming and machine learning. The key here is that in the traditional programming, the program is designed by humans, whereas here we have data and then a learning algorithm that learns the right program to execute or predict or infer the output. So that is the key difference here. And you hear a lot of buzzwords these days about machine learning. One of the biggest advances these days in machine learning is deep learning and neural network. And here's one view of it. Deep learning and neural network is a subset of the machine learning algorithms in the bigger machine learning families of algorithms. Right now, the biggest advances comes into supervised learning with neural networks such as RNNs and CNNs. So where did the brief history of deep learning can date back to neuroscience research, actually. Well, first, there was in the 50s, there was ideas from Rosenblatt about perceptions of connecting neurons, looking at neuroscience data. And the important work came in from Hubel and Wiesel as neuroscientists who tested out the cat neurons in the primary visual cortex and learned the hierarchical structure of neuronal architecture. That laid the groundwork for modeling the hierarchical neuronal architecture in the 80s, starting from neocognitron by Kunihiro Fukushima. And then one of the most important work was convolutional neural network by Yang LeCun in the 90s and 80s, where the learning rule was unified under backpropagation by people like Jeff Hinton. And then perhaps some of the students here know 2012 was the defining moment of the renaissance of deep learning by this paper by Jeff Hinton and his student Alex Kruszewski called AlexNet, which is really it was more or less similar to the 90s work in convolutional neural network, but this particular paper combined three really critical ingredients that really set off the avalanche of deep learning. The first ingredient is the neural network algorithm. The second ingredient is big data. Lots of work from many people, including my own lab. And then the third ingredient is hardware, the GPUs for parallel computing. So the convergence of these three important ingredients really was set off this really remarkable renaissance and revolution of today's deep learning and artificial intelligence. But that's only the tool part, the hammer part. We still have to solve some of the fundamental questions in AI. So now that we have this machine learning hammer, let's go back to Terry's the structure of the AI operation, which is solving the three problems: syntax, semantics, and inference. I'm just going to offer a few examples to show the progress, mostly a little bit Stanford-centric, but still give you a flavor of what's been happening. So a lot of work in the early 80s and 90s and early 21st century has focused on syntax understanding in the visual world, mostly 3D structure of the visual world. So this is a Stanford work, very famous one by Professor Mark Lavoie, Digital Michelangelo project, that shows how we can do 3D reconstruction. You might not have heard of this work, but you have heard of self-driving cars. So that 20 years of 3D vision, visual reconstruction research have laid the foundation for today's self-driving car technology. So that's a very important, important work. And then after the 3D vision era, computer vision and machine learning start to focus on semantics. That's a really important problem. Image classification, object detection, image understanding. That's when ImageNet from my lab played a role in this era of research, where we put forward challenges to ask worldwide researchers to participate in the research of ImageNet challenge. I only have 1 minute? Oh, wow. All right. Okay, so I'm just gonna go really fast, because ImageNet, this is where you now see Google Photos, Facebook tagging, and e-commerce uses this technology. Of course, there's starting to combine syntax and semantics, and this is a really fun work from Stanford. This is the technology that's going to get us AR, VR, and I'm not going to talk more about that. So I was going to talk about two work, but at this point I just flipped through. So currently my lab is focusing mostly on combining vision and language. We think this is really towards realizing Turing's dream and really Terry's dream. And on this front, we recently have two work. One is a data set that benchmark not the semantics like ImageNet, but the syntax and the inference of vision and language. This is a collaboration with Facebook of a synthesized block world and how we can benchmark the deep learning algorithm. I'm not gonna talk about this, so let me just fast forward. The last work I was going to talk about is story writing to bring out the semantics and some syntax of the pictures. Last year I talked about writing one caption, but this year we have taken this further and start to write multiple stories from a scene and eventually generating paragraphs of images, and that's the latest work I want to share with you. So at this point, I see Margot here, so I will stop at this point. Thank you.
Oh, thanks so much, Fei-Fei. I do want to point out that Fei-Fei maintains a really informative website as well, with beautiful publications, and so it would be easy to look up a little bit more. So we'll start with the Twitter question now. We have just 2 minutes for some questions, Fei-Fei.
So we have two related questions. One is, how do you prevent teaching artificial intelligence our unconscious biases? And then how do you prevent, identify, and then cleanse the bias from the artificial intelligence?
That's a great question. I think there's an increasing awareness of bias introduced to data. I like to make an example. Just type the word grandma in your favorite image search engine. You'll see the bias already, or any word that comes to your mind. I think, how do we prevent? I think awareness is a huge part of it. For example, NIPS already has workshops to discuss data bias. There is a lot of research labs that are starting to pay attention to this. We need more awareness. We need more research to look at the bias of data and to combat the bias of data. That's an important first step.
Hi, thanks for a great talk. You talked about how machine learning algorithms have allowed us to transcend the limitations of role-based systems, but with that increased flexibility also comes a lack of safety and an inability to provide the kind of guarantees on the behavior of the system that you would be able to provide under a role-based system. Do you think that there's still a role for role-based thinking in guaranteeing AI safety, or do you think that can also be provided within the framework of statistical learning, machine learning?
So I think that's a great question. I think there's a lot that's packed into it. So rule-based system is not necessarily safe. So safety, security attack comes under different possibilities. So so I think so we need to dissociate the issues of rule-based systems is not really, or the strength of rule-based system is really not about its safety and security. It's more about the inference. On the other hand, I agree with you that AI and security is really an increasingly interesting topic. For example, there is a lot of research on adversarial examples to AI systems. There is also work on how do you because looking at the inference behavior, infer back what the data or the features of the data is doing. And there is a recent work from Google Brain of how do we de-identify like healthcare or sensitive data. So all these are really important areas of research. But you also asked the question of, is there a role for rule-based system to play in today's statistical learning? My hunch is there is actually, because we still are very far from understanding what's knowledge representation, what's inference under structured knowledge, and this might also, combine ideas from the earlier work.
Great. Well, thanks so much, Fei-Fei, for
thank you.
coming and joining us. Wonderful.